Hello, I am Juneyoung from Seoul National University, and today I'm going to talk about problems with undefined behavior in LLVM and introduce our solution to the problem. This is joint work with Peephole from Seoul National University, Azure Systems, Google, the University of Utah, and Microsoft Research. First of all, I briefly explain the topic of this talk. Intermediate representation in modern compilers, or simply called IRs, use the notion of undefined behavior to justify validity of more optimizations. However, their undefined behavior models, in particular LLVM IRs, are complicated and also inconsistent with even some textbook optimizations. In this talk, I will introduce our new undefined behavior model that is simpler and, more importantly, fixes such inconsistency. First, let me introduce what undefined behavior is and what are the problems with it. To motivate the notion of undefined behavior, let's look at the following Peephole optimization example, where we use the C syntax for representing IR programs just to help understanding. Here, P is a pointer variable and A and B are integer variables. The source program on the left compares P plus A and P plus B and outputs the result. This can be optimized to the target program on the right that only compares the offsets A and B. This is beneficial because it removes two addition operations here. This Peephole optimization looks valid, but it can go wrong in certain situations. For example, suppose that P is a large number, A is 0x100, and B is 0. In the source, P plus A overflows and it becomes 0. And P plus B does not overflow, thus the result of the comparison becomes false. However, in the target, A is bigger than B, thus the comparison result becomes true. So, this optimization changes the behavior of the source program. To justify the validity of this optimization, we can define pointer arithmetic overflow as undefined behavior. Undefined behaviors are kind of erroneous behaviors that must not appear in well-formed programs. Then, compilers are allowed to preserve only well-defined behaviors because we can assume that we compile only well-formed source programs. In this example, since pointer arithmetic overflow is now undefined behavior, this optimization becomes valid because the source program raises undefined behavior, which does not need to be preserved. As you see in this example, undefined behavior appearing in the source program is helpful to compilers because it makes more optimizations valid. However, on the other hand, undefined behavior appearing in the target program may make more optimizations invalid. To see this, let's look at the following loop invariant code motion example. The source program on the left iteratively initializes the array A with the address P plus 100 up to the length n. Since the address P plus 100 remains the same during the iteration, the compiler takes the addition operation out of the loop, as shown in the target program on the right. Here, P plus 100 is computed and stored in Q before starting the loop, and Q is used during the loop. This optimization looks fine, but it can also go wrong because we define pointer arithmetic overflow as undefined behavior. To see this, suppose n is 0 and p is a large number. In the source, nothing happens because n is 0 and thus the loop does not iterate. However, in the target, pointer arithmetic overflow happens before starting the loop. Thus, the target program produces undefined behavior. This makes the optimization invalid because it transformed a well-defined program into an ill-defined program. These two examples illustrate pros and cons of undefined behavior. Undefined behavior in the source may make optimizations valid, which is a pro, while undefined behavior in the target may make optimizations invalid, which is a con. The problem here is to lift this downside of undefined behavior. Now let me explain how LLVM is handling this problem. To see this, let's look at the problematic example of loop invariant code motion again, where undefined behavior appears in the target program. The reason for this optimization being invalid is simply because pointer arithmetic overflow is defined as undefined behavior. In order to relax this situation, LLVM introduces a weaker form of undefined behavior called poison value. Then it defines pointer arithmetic overflow to produce a poison value instead of immediately raising undefined behavior. Poison is a normal value that can be stored, passed, and propagated, but can also raise undefined behavior if it is used in an essential way, such as dereferencing a poison address. In other words, poison can be seen as a form of deferred undefined behavior. In this example, Q stores a poison value due to the pointer arithmetic overflow, and then Q is never used. Therefore, undefined behavior does not occur in the target program. In summary, LLVM fixes the problem of undefined behavior appearing in the target by weakening undefined behavior into poison for certain operations such as pointer arithmetic overflow. On the other hand, you may wonder whether relaxing overflow from undefined behavior into poison does not cause any trouble in the Peephole optimization example, where undefined behavior played a good role by appearing in the source program. Previously, the overflow raised undefined behavior immediately, which made this optimization valid. Now, the overflow yields poison instead of undefined behavior. And the comparison with poison is defined as poison in the LLVM semantics. That is, comparison simply propagates poison. Finally, outputting poison is defined to raise undefined behavior in the LLVM semantics because we cannot propagate poison anymore. Therefore, undefined behavior eventually happens in the source program, so relaxing overflow from undefined behavior into poison does not cause any problem in this example. To summarize, LLVM relaxes certain operations such as pointer arithmetic overflow from immediate undefined behavior to poison in order to make more optimizations valid. The idea behind poison is that first, poison itself is no harm. Second, poison can be propagated. And third, poison can raise immediate undefined behavior if it is used in an essential way. For example, addition with overflow creates a poison value, and comparison propagates poison. And outputting poison raises undefined behavior. One important point here is that the semantics of each operation on poison is fixed. For example, comparison on poison always produces poison, while output on poison always raises undefined behavior. Since the semantics of poison is fixed for each operation, when poison is too strong, there is no way for a compiler to weaken it. This can be problematic for certain optimizations. To illustrate this problem, let me give you a concrete example. This example will show you that fixing the semantics of branching on poison is problematic. Let's look at the following optimization called global value numbering, simply GVN. GVN may replace the use of variable x with that of y under the if branch on the equality between x and y if this replacement somehow enables further GVN optimizations. This optimization looks okay because it happens only after x is checked to be equal to y. However, its correctness depends on the semantics of branching on poison. To see this, let's suppose that x is 0 and y is poison. Then, the result of the comparison becomes poison. If we assume that branching on poison somehow proceeds to execute further, then the semantics should allow to non-deterministically take either the if or else branch because the real representation of poison in the hardware might be either true or false. When the source program enters the if branch, it uses 0 from x. However, when the target enters the if branch, it uses poison from y for the same use because x is replaced by y. In this case, it is possible that the use of poison in the target may raise undefined behavior, but the use of 0 in the source may not raise any undefined behavior, which makes this optimization invalid. Therefore, to validate this optimization, we should define branching on poison as undefined behavior. This semantics makes both the source and target programs to raise undefined behavior at branching on poison, and thus GVN is validated. Okay, this semantics of branching on poison as undefined behavior validates GVN. However, the same semantics may cause trouble for other optimizations. To see this, let's look at the optimization called loop unswitching. The source program on the left contains a branch inside the while loop and suppose that the branching condition cont does not change during the iterations. Then, The compiler can hoist the branch out of the loop as you see in the target program on the right. This loop unswitching looks correct, but it can go wrong because branching on poison is undefined behavior. To see this, suppose that n is 0 and count this poison. The source program does nothing because n is 0 and thus no iteration happens. However, in the target, branching on poison happens before starting the loop even if n is 0, thus it raises undefined behavior. Therefore, this loop unswitching becomes invalid because a well-defined program is optimized to an ill-defined program. So the conclusion is that to validate the loop unswitching, branching on poison must not be undefined behavior. This conclusion contradicts the conclusion from GBN that branching on poison must be undefined behavior. Therefore, we can easily see that whatever semantics we give to branching on poison, it will invalidate at least one of the two optimizations, GBN or loop unswitching. The previous examples show that supporting both GBN and loop unswitching is inconsistent. Indeed, we found a real miscompilation bug in the LLVM compiler due to this inconsistency. We reported this bug and it is currently being discussed in the community. However, no solution to fix this bug has been found yet because it is due to the inconsistency of LLVM. So far, the LLVM community has accepted this inconsistency rather than choosing to back out optimizations that are known to be inconsistent. There are other inconsistencies as well. This is just one example. Now, I will show you how we can fix this inconsistency thereby supporting both GBN and loop unswitching. This diagram shows the hierarchy of semantic entities used for representing undefinedness in LLVM IR. Lower ones are more defined than upper ones. Note that LLVM also supports an undefined value which lies between poison values and fully defined values in order to validate more optimizations. However, the interaction between poison value and undefined value is quite complicated and is still inconsistent with optimizations such as loop unswitching because the semantics of poison is fixed. On the other hand, we take a simpler approach. We keep only one notion of deferred undefined behavior, which is poison value. We eliminate the undefined value and introduce a new instruction called freeze that converts poison into a fully defined value that is chosen non-deterministically. Using freeze, compiler can selectively make poison more defined. In other words, freeze gives a mechanism for compilers to weaken poison. Using this mechanism, we can fix the inconsistency with GBN and loop unswitching. Let's look at the form of a simple definition of freeze first. The freeze instruction takes one argument, say x. If x is a defined value, freeze x returns the same value x. But if x is a poison value, freeze x non-deterministically returns an arbitrary defined value. Now, I will show you how freeze can fix the inconsistency with GBN and loop unswitching. Let's look at the loop unswitching example again. Defining branching on poison as undefined behavior was needed to support GBN, so we keep the previous definition. Now then, this loop unswitching may be invalidated. When n is 0 and the condition is poison, the source program does nothing, but the target raises undefined behavior due to branching on poison. Now, the compiler can handle this problem by inserting a freeze around the condition. Since the freeze non-deterministically converts poison into defined values, freeze_con can yield either true or false, but never poison. Thus, the branch performs a non-deterministic jump, not undefined behavior. This way, the loop unswitching can be validated. To summarize, using the freeze instruction, compilers can stop propagating poison, thereby preventing undesirable undefined behavior from happening. For optimizations like loop unswitching, we can freeze poison to prevent undesirable undefined behavior from appearing in the target program. In contrast, for optimizations like GBN, we can allow poison to raise undefined behavior in the source program by not inserting any freeze. Since compilers can selectively tame poison, our approach is flexible enough to handle most of the problems related to undefinedness. As a further example, we show how freeze can re-enable an optimization that used to be supported but is currently disabled in LLVM due to this inconsistency. This optimization hoists division out of a loop. In the source program, dividing 100 by k is performed in the loop. It can be hoisted out of the loop because its denominator k is a result of bitwise OR with 1, and hence it becomes non-zero. This optimization looks fine, but it can go wrong in the LLVM IR semantics. To see this, suppose that x is poison and n is 0. Then bitwise OR with x propagates poison, and hence k becomes poison. In the source, nothing happens because n is 0, and thus the loop does not iterate. However, in the target, division by poison happens before starting the loop, and it raises undefined behavior. Due to this inconsistency, currently LLVM does not support this optimization, which used to be supported. Now I will show you how we can fix this problem using freeze. First, we insert freeze around x in the target program. Then, freeze x returns a defined value. Thus, bitwise OR with 1 becomes non-zero, and the division does not raise any undefined behavior. This way, we can make this optimization valid and make LLVM support it again. So far, I introduced our new semantic model using freeze. Now I'll briefly show you how we implemented our model in a recent version of LLVM infrastructure. First of all, we targeted LLVM 4.0, which was released 3 months ago. And we added the freeze instruction into LLVM IR. Then we fixed several bugs using freeze. As I have shown you before, we freezed the loop unswitching bug. Besides this, we also fixed our other problems with translation of C bit field to LLVM IR and several inst-combine optimizations. You can find more details in the paper. Of course, there might be more undefined behavior-related bugs in other optimizations that we have not looked into. However, we believe that our approach is flexible enough to fix all those bugs. To see the impact of freeze on performance, we tested our implementation using the standard benchmarks, namely SpecCPU 2006, LLVM nightly tested, and large single-file benchmarks, which are 4.6 million lines of code in total. The large single-file benchmarks are mainly used to test compilation time and memory usage. As you see in the slide, changes in compilation time and compilation memory consumption, generated code size and execution time are small, and we believe they are all within the noise. In particular, it is normal that execution time results fluctuate a bit when a new instruction is added to an IR because some optimizations and heuristics need to learn how to handle the new instruction. We did only a fraction of this required work, but the results are already reasonable, which shows that our semantics can be deployed incrementally. So, our performance evaluation shows that freeze can fix the problems with undefined behavior without significant slowdown. In conclusion, the undefined behavior models of modern compilers, such as LLVM, GCC, Microsoft Visual C, cannot support even some textbook optimizations, such as global value numbering, together with loop unswitching. We propose a new model with the new notion of freeze and demonstrate that it can solve the problems. Also, our experimental results show that freeze has little impact on performance. Thank you for your attention.
We've got time for questions.
If you just move a simple load outside of a loop, you already potentially introduce a data race, right? Which potentially introduces undefined behavior if you view this as a source-to-source transformation. How does LLVM ignore that, or how does it deal with that issue?
Oh, it is kind of an implementation detail. So, LLVM kind of canonicalizes the loop, so it has preheader. So, preheader, and there's a preheader block and header block, and it has loop blocks. So, the difference is that preheader is the entrance to the loop, so the block can be executed even if the n is 0. but header is always executed even the header block is not executed if n is 0. So actually, this kind of hoisting happens to move the load into the header block. Yes.
Hi. So one thing that I'm a little bit confused about in your work is what is adding the freeze instructions? Is each optimization adding freeze instructions where it thinks it needs to add them? Or is it based on source level annotation, or how does that work?
Okay, so your question means that the compiler has to manually add freeze to the place where it is needed? Is it right?
Well, so you have this mechanism that takes a poison value and then sticks in some random concrete value for it, right?
Yes.
So then my question is what is putting in the freeze operation? Yeah. Like in this case, loop unswitching required to freeze right. Loop unswitching required to freeze the branch condition. So if potentially the compilers can introduce undefined behavior which didn't exist in the source code, then it has to put the freeze. So is the question? So I think what you're saying then is that when an optimization can potentially add undefined behavior that wasn't originally there, it can put a freeze in.
Yes, right.
To make it defined again.
Yes,
is that
right.
correct?
You are correct.
Okay. All right.
Yeah.
Thank you.
Okay.
Okay, other questions?
Just for my curiosity, what is the reaction from the LLVM team?
Yeah, actually, so there are authors who really works in the LLVM community, and there's a kind of LLVM mailing list that has that performs that kind of discussion actively, and actually the authors wanted to deploy the freeze instruction into LLVM IR semantics, but actually changing the IR is quite a big thing. So people wanted to know whether we really needed to add this instruction. So we published a PLDI paper. Yes, right. It is kind of social process. Yes.
You think it did anything right?
Pardon?
Really nice talk.
Thank you.
I was wondering, so it seems like that for each optimization you manually inspect it and then decide where it needs to put it. Did
Yes.
you have any thoughts of adding some, I don't know, formal, maybe adding a proof or like giving some sort of mechanism to understand from the structure of the optimization where is it needed or even if it's needed at all? Just a thought.
Actually, there's a tool called Alive, which is kind of a tool that automatically verifies simple Peephole optimizations. And we can put kind of optimization into the Alive tool. And if sometimes it can say that, oh, this optimization is wrong because the source doesn't have any undefined behavior, the target has undefined behavior, this kind of thing. So maybe, yeah, there are several kinds of optimization tools as far as I know. Yes.
Any final questions? All right. Thank Juneyoung again.